Well, good morning to you all. I'll be sharing this session. So I'm Laurent Jolivet. I work at Sorbonne University, and I have been in Xavier Le Pichon's team during 11 years at ENS, just nearby. So in this session, we have a number of talks about lithospheric, well, the behavior of the lithosphere, its displacement, creation, deformation. And we start with Mathilde Cannat from IPGP, not far from here either. And she has spent a long part of her career working on 50,000 kilometers of plate boundaries and more specifically slow-spreading ridges. So after the discovery of mid-ocean ridges, their mapping, their understanding as divergent plate boundary, well, divergent boundaries at the beginning by Marie Tharp. We have another woman focusing her life on ridges. So the floor is yours, Mathilde.
Thank you. The title of my talk is focusing on how you form new lithosphere at mid-oceanic ridges, but I'm going really to focus on what magma fluxes have as an influence. But I will start with a kind of the beginning. So there will be several slides that concern the beginnings when magma fluxes were not the issues. And then we will see that magma flux and spreading rate become really the issue in understanding mid-oceanic ridges. And towards the end of the talk, it will be mostly slow spreading ridges, because that's what I work on. And it will be mostly recent results with recent PhD students, and particularly with the work of Jie Shen, who was a PhD, then a postdoc, and is now a colleague. And we work together with Jean-Arthur Olive to investigate melt fluxes at mid-oceanic ridges. So the first slide shows kind of in-fashion projection, recent type of projection to look at the mid-oceanic ridges. And here is, I think, the very first picture of it's across the Atlantic Ocean, and it actually represents oceanic spreading, because these authors, they believed that all the evidence pointed towards the ridge axis being younger and then going back, and you can see they had already the notion of the thickening of the sediments, etc. And they also had some volcanism. And but the problem was at that time that there was no knowledge of how long this spreading took, and there was this kind of extremely weird expanding Earth theory that was quite widespread. And so they said, okay, we see spreading, and it might be because the Earth is very slowly expanding, and therefore it could have taken billions of years for the Atlantic to form. Okay? And then I just show, it's a little bit later, it's in 65, and the key year really is 66. In 65, they produced this beautiful physiographic map of the Indian Ocean, and I put here the same map from the relatively recent satellite altimetry-derived topographic map, and you see that it's remarkably accurate. And but at that time, what was happening at that time is that Harry Hess had published this model in '62. That was a convection model in which the ridge was the upwelling, the zone of upwelling. And you notice that it's a very conceptual model. It doesn't really take into account the geological observations, like the fact that there were basalts. Everything is serpentinized. And it was a big problem, because it had, in order for this to apply to actual data, you had to be able to imagine that you would have upwelling things along all the ridges. And in a way, a model that is widely recognized as the first one to really propose plate divergence and plate tectonics was it's a danger when a model is very conceptual and when people looking at the models have a very, I would say, positive type of philosophy of science in which things are right or wrong. Okay, and it's like in physics, if you make an experiment and the prediction of your proposed equation doesn't work, then the mechanism is wrong. In natural science, it's rarely the case, and actually it's right, but it's just that, as we all know now, the connection between convection and plate tectonics is much more complex. Okay, so in 65, in the paper they discuss and they say no. It doesn't work. It cannot be plate spreading, ocean spreading, and plate tectonics because we cannot have fit upwelling limbs of mantle below all of these things. And you see also that during the same key period, you had the Wine and Matthew paper. The Wine and Matthew paper clearly said we have spreading and clearly proposed that it was much faster than the expanding Earth. And in any case, everybody with kind of physical knowledge would say that the expanding Earth theory doesn't make any sense. There were some papers trying to understand the energetics behind that, and it was just crazy. And but the problem is that at that time there were no age data. And it's only with the work of Cox and collaborator in 64 that Wine in 66 was able to fit his Middle-Sneak Ridge magnetic anomaly pattern to actual very recent ages. And of course, in the meantime, the seismicity at subduction was becoming so evident that everything kind of collapsed and crystallized in the brain of everybody. And by 66, everybody agreed that you had plate tectonics. So what was Xavier Le Pichon doing at that time? Well, Xavier was part of as a junior member of the Lamont group that collected an amazing amount of data in all the ocean basins and focusing on Middle-Sneak Ridges. And they published between 65 and 64, he published with his co-authors of Lamont 5 papers that cover all the aspects, seismicity, magnetics. And here I show you a figure from this focusing on heat flow paper. And you see that they tested the upwelling limb and the convection theory with this model, and they produced this. They predicted this thermal system, and they predicted this heat flux thing. And the fact is that, of course, as we all know now, the heat flux over ridges is lower because there is hydrothermal circulation. And so they said, well, we get much too low heat flow data, therefore it cannot be an upwelling limb. So again, this kind of brilliant conceptual model missed its purpose because it kind of led people to think that it wasn't what it was. And by the way, notice that Harry S. also didn't even imagine that the water in the ocean could play any role because when he serpentinized the mantle to produce the crust, well, he takes the water from the mantle. He doesn't take the water from the ocean. So I think it's something to make us very humble that very, very brilliant people can get completely wrong. And of course, by 66, and unfortunately this paper was published in 66, and so it took a little bit more time, maybe without internet, for news to crystallize. But by 68, Xavier published his famous seafloor spreading and continental drift paper, and that was it. Everybody was convinced. Okay, so I'll start with a few slides on what happened after, with periods for each type of topic. And I would say that 72 and 79 is really the discovery of this key component that was kind of putting everybody in trouble before, is the discovery of Middle-Sneak Ridge hydrothermalism. First, it was predicted from heat flow data by Lister. Okay, he understood that the only way to explain this heat flow data was to have hydrothermalism. And then it was discovered at the Galapagos Ridge, and then a submersible was able to observe the life and the actual venting. And in 73, 78, about the same period, we see Xavier as a key player again, because by that time he had gone back to France and been one of the key players in putting together the Centre Océanographique de Bretagne, which later became Ifremer. And as the leader of this Centre Océanographique de Bretagne at that time, he co-signed the contract with Woodsole Oceanographic Institution to put together a multi-cruises effort to map the mid-Atlantic ridge and to explore it with submersible in the famous area. And they were able, they discovered quite a few things, but they clearly were able to show that the mid-Atlantic ridge actual valley is formed by normal faults. And there was one of the first, I think it's the first mechanical, or at least, anyway. So Franchetot worked with Taponnier, and Taponnier was at that time working on continental rifts, and they produced this model that is very simplistic, not very rheologically reasonable, but shows one thing, illustrates one thing, is that you need a thick lithosphere at the ridge axis in order to make the actual valley. And that's a key thing, because it means that that you need a lot of you need the ridge to be relatively cold. And then in the years later, rapidly, there was more mapping. At that time, it was not easy to map because it took a long time. They didn't have the multi-beam systems. And they were able to show that there is an inversion of topography between fast-spreading ridge and slow-spreading ridge. Fast-spreading ridges are basically elongated volcanoes. And you can see that with early on, they could see that with the seismic reflection, showing that you had a reflector at less than 2 kilometers below seafloor that could not be interpreted reasonably by anything else than magma. So you had a thermal constraint on the thickness of the lithosphere on axis, because this had to be around the 1,000 degrees isotherm. And then the actual valley, the first real constraint on how thick the brittle lithosphere could be, came from an earthquake study with the first OBSs that showed that you had earthquakes down to at least 8 kilometers below seafloor. So you had a brittle lead of 8 kilometers. And using these constraints, the Shen and Morgan were able to produce a simple conductive model of the mid-oceanic ridges, predicting the isotherms. And then what they did is that they adjusted conductive cooling, and they approximated it just by enhancing conduction. And they kind of fitted it so that the isotherm would fit the data. So you see the 1100 degrees isotherm put to fit the actual magma length depth at fast ridges, and the 750 isotherm fit to get at the deepest thing. And one of the big results of that is that in order to fit it, you have to multiply the conduction of the actual region by 8. So what it means is it gives us an estimate of the proportion of heat that is extracted by hydrothermal systems at mid-oceanic ridges. It's at least 8 or 10 times more than the conduction alone. Clearly, what they used as the motor, the heat, really comes from magma, okay, at ridges. And so they used a spreading rate dependent magma heat flux. And what was this spreading rate dependent magma heat flux based? It was based on the recognition, even at that time, but this more recent picture has more data on it. When you look at the seismic crustal thickness along and close to in ocean basins, there is a spread, but you see that the average at all spreading rates is about 6 kilometers. So the idea is that whatever at the rate, you have to have enough magma to produce a 6 kilometers thick layer, and that's what we call the melt flux. And here is a small calculation that you can do. If you take the total length of mid-oceanic ridges from a very good paper of Bard with all the plate boundaries and their relative displacement, you get 65,000 kilometers or so at an average spreading rate of 41 millimeters. And if you use that to calculate the total magma flux at mid-oceanic ridges, you get about 16 cubic kilometers. And this, if you divide it then by the number of kilometers, you get a magma flux of 247 cubic kilometers per million year. And you can calculate the corresponding heat flux, and it's about 2 terawatt for the entire ridge system and 31 megawatt per kilometer for the ridges on average. So just to keep these numbers in mind, if we now look at this diagram, it's very simple. It's just the melt flux in cubic kilometers per million year as before, and here it's the equivalent magmatic thickness, so it would be derived from seismic data. And what you see is when you calculate the melt flux for all these different crustal thickness, the spreading rate is here, the East Pacific rise is here, the global mid-oceanic ridge is here, and what you see very rapidly from this diagram is that there is no way for slow spreading ridges, like the Mid-Atlantic ridge here, to ever get as hot as the fast ridges, even if it had enough magma to make a 12 kilometers thick crust, or even you could go on. Okay, so the conclusion is that slow ridges are always colder than fast ridges because they always receive way less magmatic heat per unit time. Okay, and so it's something that is, and I will stop talking about fast ridges now, but it's something that is clear. There is no way for a fast ridge to have an actual valley. There is no way for a slow ridge to have the equivalent feature of actual high. So another thing that is very clear is that the magma fluxes and the thermal regimes vary a lot along slow spreading ridges. And to illustrate that, I show you 3 examples of slow spreading ridges with the compilation of what we know of the geophysical system. One has a crustal thickness of 9.5 kilometers, so it's anomalously magmatic, but it's a very slow spreading rate. And you see that it has a low velocity zone, so presumably some kind of magmatic mush, and therefore the lithosphere, the actual lithosphere must be quite shallow, at least in this place, not here. Another example, and I'll come back to this one later, is because it's a place where we've put, there is a very active hydrothermal site, and we've put an observatory there, but it's the Lucky Strike location, and it's also slow spreading, but a bit faster. It's also more magmatic than the average, 7.5 kilometers, and in this place we have a localized actual melt length at 3.54 kilometers. So you can, but what we see is also that we have some earthquakes deeper, and so it means that it's a relatively 3D structure. And then there is the last example. It's also at the Southwest Indian Ridge, very slow spreading, but here it's really, it's kind of a monster in the Mid-Oceanic Ridge system, because it's a portion of the ridge that receives almost no magma. And in this place, of course, you exhume, you have very, very little magma. And what you have is earthquakes that go down to about 15 kilometers below seafloor. So you have a thick lithosphere. So very, very contrasting systems with at very different melt fluxes. Okay, I'm going back to the more historical approach after this intermed, je ne sais pas comment on dit. So in the late 80s and 90s, the thing a lot happened, okay, but the thing I want to insist on, because it makes sense in the title of my talk, is that it was discovered that slow ridges have spatially variable magma fluxes, and also that they expose serpentinized peridotite. And the slides on this subject will be numbered. So the first slide illustrates how slow ridges are segmented. This is the bathymetry, and you see that you have segments of the bathymetry. And this is the gravity, and you see that you have gravity laws in the center of most segments. And these gravity laws are interpreted as thicker crust. And of course, gravity is not enough to make sure that it is indeed thicker crust, but in 93, there was the first dedicated OBS study at a segment of the Mid-Atlantic Ridge, and the authors were able to show that indeed the thinning of the crust predicted by gravity is observed in the seismic data, and is even more pronounced actually. And so you have a crust in the middle of the segment that is actually thicker than average, and a crust in the extremity that is thinner, so that if you take the whole segment, so typically 30, 50 kilometers on average, then you get back, in most cases, to the 6 kilometers average. Okay, and then the exposure of peridotites. So what happened is that there had been quite a few dredges that came back with peridotites. And people were saying, because people had been dredging mostly transforms by that time, and at transforms you get a lot of peridotites. But there were some dredges outside, and there were also a few drilling holes, ODP drilling holes, that had recovered, the peridotites are in black. Okay, and they had recovered peridotites at various levels, sometimes directly underneath basalts, sometimes over basalts, so that's clearly a mass wasting system. And this is how we interpreted it after looking also at imaging the field relationship at alpine ophiolites. So imagine that you had intrusions of gabbros in serpentinized peridotite and small volcanoes and lava flows, and also mass wasting to try to explain these field relations. And actual peridotites were observed by submersible in '87 on the Rift Valley wall away from transforms, so that was really a key thing. And then there was Henry Dick was studying a lot of gabbro samples and from all over, and he argued that he was not alone, but the petrological evidence kind of converged to the idea that these gabbros had crystallized in intrusions, not as a persistent mush, but as intrusions, and these intrusions could be in previous gabbros or in peridotite. And he had this sketch where he represented the segmentation, and this magmatic crust is thinning towards the end, and kind of therefore you have peridotites outcropping at the end. But the problem is that you don't get mantle peridotites at the seafloor without faulting. Okay, you don't cross the thick lithosphere. You don't cross 10 kilometers of brittle lithosphere just because. I mean, you need faults. So that's where what I propose, based on looking at on recognizing that you had a lot of intrusions of gabbros in the peridotite, and that you needed faults in order to bring peridotite to. Well, we actually needed faults for more than that. You needed faults if you had a thick actual lithosphere. If your actual lithosphere is thicker than whatever magma you can inject, then you do need faults in order for the plates to move apart. And so the idea was that magma does not form as a continuous mushy lower crustal layer, that we know, but discrete intrusions potentially over the whole thickness of the lithosphere. And then plate divergence requires substantial normal faulting that brings the peridotite gabbro mixture up through the actual lithosphere. And the idea was that if you found from geophysical data that the brittle actual lithosphere is thicker than the accumulated melt column, then the crust is going to be composite. It will include both tectonically uplifted serpentinized peridotite and magmatic rocks. But at that time, of course, the big problem was that none of us knew what these faults looked like, because we had this conception of faults having to be like steep scarps. So people would map the steep scarps all over the place. But it turns out that the actual big faults that bring these mixtures to the seafloor, they are not steep when you see them at the seafloor. So anyway, so this was a completely conceptual model. This one was a kind of model that was inspired by looking at continental detachment faults that are often working as low-angle faults. But it was also completely disregarding our knowledge of the fact that the exhumation of the peridotites was not during amagmatic periods. It was not like you form the crust and then you thin it. Okay, it's that you form a composite crust, and so they proposed that, but none of us could say, okay, I see this here or there. And then there was this cruise in the Atlantic, the Mid-Atlantic ridge is here, and they were not looking for that at all, but by chance they mapped. At that time they already had some kind of reasonably good multi-beam data. And they were able to map this dome here, and they interpreted this dome that exposed serpentinized and gabbros as the exposed fault surface of the fault that had exhumed these things. And so that was okay, and they proposed to call the fault responsible for this dome an oceanic detachment, and they also noticed that there are some striations or undulation on the dome that are parallel to the plate motion. Okay, so they proposed that, but really I think the key, and that's why I stopped the period at 99, I think really the key, when everybody accepted that this was actually the case, that these strange kind of horizontal domes were the exposed fault surface that are responsible for exhuming the peridotites, is after numerical modeling by Roger Buck and Luc Lavier, and they were because they were able to actually reproduce the exact, I mean, a very, very similar system with the same type of domal topography, simply by using a rheology in the fault that becomes weaker as deformation increase, which we as geologists really liked, because that's what we see. All the fault rocks, they always have a strain weakening mechanism in them. Okay, and the way it works is that the fault initiates, and then what happens is that as the fault moves on, you flexure the footwall and the hanging wall, and that applies a force on the fault that is counter to the movement. The only way to counter this force is to weaken the fault. Okay. And another thing that was really interesting in the model was that it was problematic to have a low-angle fault, because if you want to have, you are at a plate boundary, okay, so you want to separate America from the European plate, and you're not going to do that with a low-angle fault, okay? It has to plunge down to the asthenosphere. and their model really looked had a steeply dipping fault, and this was for some years, and then there was kind of confirmation from actual data with a seismic microseismicity experiment at the Mid-Atlantic Ridge again, showing that you had a distribution of earthquakes that you could interpret with a 70 degrees dipping detachment, and also some small offset antithetic faults. Okay, and so how are faults weakened in oceanic detachments? I don't have time to go into details. Actually, I'm going to be, okay. So fault rock weakening is in every case strain and fluid, be it hydrous or magma dependent. And also the fault rocks are always semi-brittle at all depths in the lithosphere. So it means that the fault system itself is there's no, it's in the semi-brittle domain. And I show it's been observed at many faults because oceanic detachment faults has this nice characteristic that they actually bring the material up. Okay, so you can sample, when you sample at the seafloor, you get rocks that have been deformed at all structural level, and with a little bit of petrography, you can figure out what temperature all the deformation were made. So I take this example, and this is the same section at 1:1, and we see that for a lot of reasons, we see the fault as a rather thick fault zone, and we can, from the sampling, we can show that you have a deep portion at the brittle ductile transition where you have grain size reduction and semi-brittle deformation of fluidotides. Then you have a portion, before you get into the serpentine stability regime, you get a portion in which deformation occurs in things that were formerly gabbroic diclets and were altered into amphibolites, and they are sheared, and you can see that the fluidotide is brittle around, okay? And in this particular region, there are very, very few of these, so that might be why you've got all these earthquakes at that level. And then you get into the upper region in which the deformation is brittle in the undeformed fluidotides and semi-brittle in shear, gouge-type fault zones. And I would just say that it's an advantage of oceanic detachment that is useful to inform other studies of trans-lithospheric faults. Is first this access to samples deformed from seafloor to brittle ductile transition, and then the opportunity to record the associated seismicity at the same place. Okay, and clearly one place where what we've learned that oceanic detachment is useful is transform faults, because after all there are the other component of the 89,000 kilometers of ridge transform plate boundary system, and fortunately there are now really a key research focus for the Morb community in at least in the US and in France. And this is an example of a deformed fluidotide from a transform. And the texture is very similar to what we've seen in the detachment. Here's the very complex, much more complex, much longer life faults. Okay, seismicity, and here is another example. I'm not going to talk about that, but there is also a potential for carbonation and for these systems to be a part of the geological carbon storage. I see that I won't have time to finish my talk, so I just go on. One question we had, and I think it's a valid question. There have been papers published saying, okay, we see amphibole in rocks that come from deep, etc. Does it mean that we have actual hydrothermal circulation in the sense of a heat flux? The evidence we have is actually that when you get hydrothermal amphibole, and this is what we get in the grain size reduction deformation in these rocks, it doesn't necessarily mean that that there are hydrothermal convection cells, and actually the hydrothermal systems in general and at ridges are good places to study them. They are very complex, and at least one big separation could be between the highly permeable upper hydrothermal circulation domain and then deeper zones in which maybe little by little, earthquake by earthquake, you get a little bit of water, or rather very hot hypercritical hydrous fluid that goes down and ends up at the base of the brutal lithosphere. And I think I will just go on and we stop where I'm finished. So that brought me to the idea that it would be interesting to show you some key characteristic of the other member, which is a real vigorous hydrothermal circulation, black smokers. And the example is at the Lucky Strike hydrothermal vent field. And this is what we've seen already with the magmatic heat flux that you can calculate from the crustal thickness and etc. And we get 21 megawatt per kilometer. And when we try, it's hard to estimate the hydrothermal heat flux from the field. We get between 200 and 1,000. So that's much bigger. And it's a general case, possibly not at fast-spreading ridges, but at least at slow and intermediate ridges. You would always need to mine heat from a long portion of ridge in order to feed your hydrothermal system. But the problem is that when you look at the dynamics of black smoker type hydrothermal circulation, you see that they cannot, for physical reasons, actually mine most of the heat elsewhere than very close to where the field is, in about a 1 kilometer radius. And microseismicity at hydrothermal systems is consistent. You see, you have this microseismicity that is interpreted as a thermal cracking of rocks, and it's within 1 kilometer radius from the zero is where the vent field is located, leading to this cartoon here. And so I will just stop here to say that actually our preferred interpretation, and the one that really makes sense, is that it does mine heat from magma over 2 kilometers, but the consequence of that is that at the time the field is active, there is way more magma provided to the ridge. And what it means is that the melt flux at slow ridges, at least, is very highly time dependent. And this is just the description of an experiment that we did to test that with a periodicity that is based on volcanic morphology, but there could be, again, very many combined scales of time variability of the melt flux. And so we try to reproduce the system with a higher melt flux, very much higher melt flux, like 15 kilometers, equivalent to 15 kilometers of magma for 100 kiloyears, and then much less for something. And what we see is that what we, as we wane and wax the melt flux, we drastically change not just the thermal regime in the lithosphere, which will have an impact on the faulting and on the magma petrogenesis, okay? How gabbros will crystallize, but we also affect the vent temperatures. Okay, and unfortunately, I've been too long, so I will leave you at that.
Thank you very much, Mathilde.